Hey guys, let's talk about a few problems out of the Achieve section 4.5, and these were all pretty darn good questions here. I really like them. The first one here, number 14 in section 4.5. It's one of these where we're going to have to use multiple uses of L'Hopital in order to work it out. You'll see the problem given was the limit as x approaches 0 of the sine of x minus 4x cosine of 4x all over 4x minus the sine of 4x, and this is, of course, as x is approaching 0. You know that any sine function of a 0 angle is 0, so we just get 0 minus 4 times 0 times what would be 1, but the whole fraction, or sorry, that whole term is 0 because of the x term in there. This term is 0 because of x, and then the sine of 0 is 0. So everything is 0 over 0 here. I use L'Hopital to figure it out. Now, one use of L'Hopital, I know that anytime I'm taking the derivative of a trig function that's containing an angle of 4x, it's going to need to be multiplied by 4. So I said, well, derivative of sine is cosine. I have to multiply by 4 since my angle has a 4x in there. I get 4 cosine of 4x. Now, when I move to the second term, I need to remember product rule. I said derivative of the first is just going to be 4, so I have minus 4 cosine of 4x, and then it would be also minus, because the second part of the product rule also takes on this minus sign, minus 4x, and then I would say times the derivative of the cosine. Well, that's going to take that minus sign and turn it to a positive, and then you also say, but you're also multiplying by yet another factor of 4 thanks to the chain rule, the derivative of the angle. So I'm getting 16x sine of 4x for the second portion of that product rule. And again, normally you keep that minus sign there, but the reason that plus sign came in is because I said derivative of cosine is going to be the negative of the sine. And then, of course, the 4 changed to 16 because you had to multiply by the derivative of the angle. So pretty good stuff there with the chain rule. In my denominator, the denominator derivative of 4x is 4. Derivative of the sine of 4x would be the cosine of 4x times 4. So I put 4 cosine 4x. Now when I'm thinking about this, I still can't evaluate these two terms just cancel in the numerator. I have 4 cosine 4x minus 4 cosine 4x. My only term in the numerator now is going to be that 16x sine of 4x. And I know that that's going to 0. My denominator is going to be 4 minus 4, so it's going to 0. So I put my simplified fraction in this step. Notice I did not put an h over the equal sign. I'm not using L'Hopital. I just simplified. But now I do need to use L'Hopital. So I'll say, well, the derivative of this numerator, once again, you need to use the product rule. I said derivative of the first is 16 times the second, plus the first 16x now times the derivative of the second, which would be the cosine of 4x times 4. That times 4 had to multiply the 16 and give me a 64x cosine of 4x. My denominator, derivative of the constant, canceled out. Derivative of negative 4 cosine of 4x would be, I know the derivative of cosine is going to be negative sine, so that's changing that to a positive. 4 sine of 4x times 4, that's where the 16 came from. So now I can say, all right, when I'm simplifying this step, I know my denominator is still 0. My numerator, this term would be 0. Sine of any 0 angle is 0. The second term is also 0 because the 64 times 0. So yet again, I have to use L'Hopital. So the derivative of 16 sine of 4x would be the 16 cosine of 4x times 4. That gives me 64 cosine of 4x. Then I go on to my next term. Derivative of the first would be 64 times the second cosine of 4x. And then the second part of the product rule would say, well, okay, now you're going to have to add 64x times the derivative of the second term. But the derivative of the second term, derivative of cosine's negative signs, that's why you get the minus sign there. And I would have 64x sine of 4x times 4. I had to multiply 4 by the 64 to get the 256 there. My denominator, similarly, I had to use the chain rule and say, well, derivative of sine is cosine of 4x times 4. That times 4 had to multiply the 16 out in front to give me the 64 cosine of 4x. Now, I know that the sine of any angle is just going off to 0. So when I try to take the limit as x approaches 0, that whole last term is just 0. But the cosine of 0 is 1. So I have 64 times 1 plus 64 times 1 for 128 in the numerator. Of course, your denominator is 64 times a number approaching 1, so it's 64 as well. We have 128 over 64 for a final answer of 2. That was a pretty cool problem. I would say it's on the more difficult end of the spectrum, but fun nonetheless. We checked that answer and it says correct. The next one I wanted to look at with you was 15. Now, in 15 here, you'll see that we have the limit as x is approaching 3 pi over 2 of the polynomial x minus 3 pi over 2 times the tangent function x over 3. Since this wasn't in our normal fraction format, I just looked at the format that it was in, and we know that that linear function, the polynomial, that's just going to be 3 pi over 2 minus 3 pi over 2, so that's a number approaching 0. The tangent, as x approaches 3 pi over 2, the tangent function is approaching 1 pi over 2. And you notice the tangent function is approaching pi over 2, it's approaching a number of infinity. So this is one of our indeterminate forms that L'Hopital should be able to help out with when the limiting value is a number approaching 0 times a number approaching infinity. In order for L'Hopital to work, though, we need to form a fraction. So that's the first thing I did, is I just said, let's put the tangent down to the denominator and call it the cotangent. Now I'm using L'Hopital's method by saying, well, let's take the derivative of the numerator, which is simple. The derivative of x is 1, over the derivative of the denominator. And you know derivative of cotangent is negative cosecant squared of that angle times the derivative of the angle. Okay, so now, especially since my numerator canceled, I'm just going to put everything up there because I know that the negative cosecant squared, that's the same thing as a negative sine squared in the numerator. And if my denominator has a factor of 1/3, then my numerator has a factor of 3. You can think of it as multiplying by 3 over 3 to get rid of that. So this simplifies down to just be negative 3 sine squared of that angle, x over 3. No reason to not evaluate it at this point. Now, if you let x equal 3 pi over 2, then this angle is going to be 3 pi over 2 divided by 3, which is just pi over 2. You know the sine of pi over 2 is just 1. Now, granted, this was sine squared, doesn't matter. 1 squared is still 1. So you end up with just negative 3 times 1 for a final answer of negative 3. And I'm positive that is the solution. We go to negative 3, check answer, correct. Next one in here I want to look at with you, number 18. Number 18, we have exponential functions in our numerator, and then you have a nice linear denominator, and we know L'Hopital needs to be used because if you just tried to plug in the 4 that you're given here in the first step, it's not going to work. You'd have e to the 4 squared, that's e to the 16th minus e to the 16th. Your numerator is 0. Your denominator would be 4 minus 4, which is also 0. So we get 0 over 0. I use L'Hopital to try to figure it out. I take the derivative of the numerator. You know the derivative of that second exponential is just 0 because that is just a number. Derivative of any constant is 0. But the derivative of the exponential function, you do have to worry about. We say derivative of any exponential function is that exponential function times the derivative of its exponent. So I get e to the x squared times 2x. Derivative of x in the denominator just gives me a measly 1. At this point, I know I can evaluate. You plug in the 4, you'll get e to the 16th times 2 times 4, which is times 8. Final answer should be 8e to the 16th. Let's try that. I say it should be 8 times, and then I'll go down here and use their buttons for the exponential function. E raised to the 16th should check out. I go to check answer, and perfect. Okay, up next, the last one that I had a question on was number 23. And notice what I've done here for 23. I've said that you cannot attack this problem directly. Yes, it is one of the formats that L'Hopital works with, because if I try to let x go to infinity, your base is going to infinity, but your exponent, 19 over infinity, it's going to 0. So this is in the format of infinity to the 0 power. That's one of our indeterminate terms, so we use L'Hopital to try to figure it out. But you can't get this into a nice fraction as it is. So what I went ahead and did, and I think it's the best thing to do, is just go ahead and let f of x equal what you're trying to take the limit of. Now, instead of directly trying to work with that, let's try to work with the natural log of both sides. So I'm using the same concept that we did with logarithmic differentiation. I'm taking the natural log of both sides. The natural log of that right-hand side enables me to bring that fractional exponent down in front, and I can say 19 over x times the natural log of x. Now, automatically, that creates a fraction. I can say, well, then that's the same thing as 19 natural log of x over x. So then, since I can't directly take the limit as x approaches infinity of f of x, let's instead take the limit as x approaches infinity of the natural log of f of x, which would equal the limit as x approaches infinity of the expression that we have right here, 19 natural log of x over x. And you can say, well, this should be infinity over infinity in this format. You have 19 times the natural log of infinity over infinity. Infinity over infinity is one of our indeterminate formats. I use L'Hopital. Derivative of the numerator, derivative of the natural log of x is 1 over x. So we just have a 19 over x for that numerator. Derivative of x in the denominator is 1. So that's the only use of L'Hopital from this step to this step. Please don't put the h over the equal sign. The only thing I'm doing is rewriting. This is simply just 19 over x. Well, as x goes to infinity, 19 divided by infinity, in fact, any finite number divided by infinity goes to 0. So what I have shown, and I've put down here, since the limit as x approaches infinity of the natural log of f of x is 0, and that's not our answer. Our answer needs to be just of the limit as x approaches infinity of f of x. Well, to get from this to what we need, you would just need to exponentiate each side. So I can say, well, then the limit as x approaches infinity of f of x would equal e to the 0, and you know e to the 0 is 1. So our final answer here should be 1. I put that in, check answer, and it's saying correct. All right, guys, I hope this helped you with these problems in section 4.5. I think these questions were excellent. Please let me know if you have any other questions. I'll be glad to help.